Hello, everybody. Welcome back. My name is Alicia from the 3D Natives team, and we're going to move on now to the next talk about polymer laser sintering, enabling applications through new materials. Welcome, Cary.
Hi, good morning.
Good morning. So Dr. Cary Baur is the manager of polymer material R&D and applications development at EOS North America. Cary's team works with customers to drive the new market opportunities through advanced laser sintering materials and offers process and design support to meet the most challenging applications. Through new materials such as polypropylene, PEKK composites, and specialized polyamide formulas, Cary's team is introducing new platforms to advance polymer laser sintering further into serial manufacturing. Cary is also very active in developing materials partnerships to provide customers with a broad material portfolio to advance their applications. So welcome, Cary. Don't forget to send your questions in the Q&A section so that Cary can answer them at the end of the talk. So I'm gonna lead you now to the talk, and I will come back to you after in a few minutes. Okay? See you. Bye.
Is everything okay there, Cary?
Yes, can you confirm that you can hear me and see my screen?
We can hear you. We cannot see your screen yet.
Cannot see my screen yet. Okay, let me just make sure.
Make sure you click into the monitor. Perfect. Wonderful. Thanks.
Okay, and can you confirm one more time you can see my slides?
Yes, we can see your slides.
Okay, thank you. Thank you, Link3D team. I'm happy to be talking to you here today. And the topic of my presentation is really going to be around enabling applications through new materials and how we approach that at EOS. And so the agenda roughly is I'm going to give a little bit of an intro into EOS, very brief, a little bit of a background into what laser sintering is. I'm sure most of the attendees here are pretty familiar with the different polymer additive technologies, what the advantages of laser sintering are, an overview of the materials, some going a little more deeper into the materials that we offer and the materials that we don't offer on demand, but we offer in more of a custom way, and how we're enabling new applications. So EOS, just a broad overview of our company, is we've been focused on industrial polymer and metal sintering for over 30 years. We're based out of Cryling, Germany, which was just outside of Munich. We have over roughly 3,500 machines installed worldwide, which is quite a large base of machines. We have roughly 1,500 employees globally, 450 engineers, and roughly 400 million in revenue. So what is laser sintering? How does it differ from other technologies? Well, the first thing is it's powder-based. So both polymer, both metal, it's a powder-based technology, traditional to how other additive technologies work. We operate from a digital file, usually an STL. This is something that would then be loaded onto the machine platform. And the way this works is essentially you're building your part in a lowering build platform. So what this means is we're recoding powder into a fine detailed layer, and then we're using a laser to scan the pattern that is within the file that we're uploading. The platform is lowered roughly every, usually most materials are 120 micron layer thicknesses. We'll recoat either, we have some machines that use rollers, some that use recoater bars, and this is how the process works over and over again until you get your part. Now, as you'll notice, the part there is encompassed in powder at the end of your build. And so essentially, there's no supports required because there's not a bunch of free weight and stresses in your material. And also you, at the end, break your parts out of your free powder that's unmelted. So then you would raise your part up to the top and then remove the powder. So what are the advantages of laser sintering? Some of these are typical of additive manufacturing in general. Some are more exaggerated with laser sintering. Lightweighting parts, there's a large material variety in laser sintering, especially in the way that we can composite our materials to lightweight materials. Obviously, through design interface, we're able to reduce more mass from parts and add mass to parts that need more structure, so that we're in that way able to lightweight parts while maintaining the performance of a part. Integrated functionality. So how can we reduce parts that typically of an assembly might take 30 different parts? How do we reduce this to reduce complexity, lead time, and costs in the supply chain and in the manufacturing assembly? And so also reducing that tooling cost and that human cost to be doing all of that work. Customization. So, sorry, I think can anyone confirm if you're still seeing my screen okay?
I can see your screen, but not your presentation.
I got a Zoho notification there.
Perfect.
Just stick with me one second, Janet. Let me know if...
Set. You're all set. Yeah.
Okay, thank you. Got it. Okay, individual parts, so we can build a relatively large amount of parts, but with a very high amount of customization. This is one of the things I'll touch on soon, and also rapid prototyping. How do we then build our designs faster, build our products faster, and validate them via testing and rework? So that's kind of the technical advantages of additive manufacturing, but the business advantages look very similar. So like I mentioned, redefined NPI process. So what this would mean is, as we're integrating new products, much faster testing, much faster validation, faster turnaround time. The design for additive consolidation. So basically, how can we improve the way that we assemble parts? How do we reduce the variety and steps it takes to make a part? Distributing manufacturing is, in a mass customized world, we can then be allowed to basically allow ourselves to distribute our manufacturing to different localities to reduce lead times, to reduce logistics costs, and also often to offer customization in an area that may not align with the needs of customers in another area. And also that just personal customization. How do we take user input data across many different industries? The sports industry is I think a very active area right now. How do we take user data and integrate that into a customized part, but also on a mass scale? So very, very simple application example I put in here just to kind of get my point across. This is a lightweight gripper that we helped redesign. Originally, it had roughly 21 parts because there was a lot of, as you could see, a lot of internal piping and hosing that needed to be in this component. And through those sides, the corners, you essentially have these suction areas that will then allow it to grip on an assembly line and move a specific part around. We were able to work with this team to design these components to internally basically integrate those channels internally in the structure, reduce it to a 3-part component, reduce the assembly and build time to 1 day from 18. And so that was a huge lead time reduction, a huge weight reduction, 86%. And overall, when you include labor, when you include lead time and costs of materials, it's over a 50% cost reduction. So why am I talking about plastics today in general? Like I mentioned, we have a robust business in metal and plastics. The reason I'm talking about plastics is we see it as a huge opportunity in the industry. So I was looking at the volumes recently of what actual additive manufacturing volume-wise in plastic produces compared to the industry, the plastic industry overall. And roughly 1 in every 100,000 pounds of material, plastic material that is produced is used in additive manufacturing. So when we're looking at this industry, it feels like it's growing, and it is growing very quickly. But there's still a huge opportunity just based on the fact that we're only one out of every 100,000 pound is going into our industry, and we think there's a lot of opportunity there. And what does plastic bring that other technologies doesn't? Brings a lot of customization ability, and a lot of ability to maybe have a base resin, but also build on that base resin by offering different compounds and different things that will allow our customers to really hone in on the application requirements that they have. So just a graph on the left, you can see this is general plastics versus steel. It's growing very quickly. We think it's going to continue to grow, and that includes standard and engineering plastics. So what's been holding AM back in the past? Why are we only at one out of every 100,000 pound in our industry? Well, it's really matching up that material choice with the machine availability is one issue. So unlocking the ability to have a larger variety of materials in your build process. There's been a slow growth of additive know-how and design compared to, I think, the technology overall, and that's something that we need to continue focusing on. Events like this are great because you actually have a much faster adoption of the technology by getting 500 people in the same room watching the same events and learning together. That really accelerates the way that we all understand additive together. And really just a mindset driving that culture. So at EOS, we do have a focus on new innovation, and we put roughly 15% of our revenue back into R&D. What that allows us to do is the things that our customers are currently working on and discovering that their needs are, is we're trying to directly funnel that into our future pipeline so that there's not a lag in our products and a mismatch between customer demand and what we're offering. So across the globe, largely Germany, and I'm in Texas. Here in Texas, we have quite a few machines, and also in Michigan, we have over 100 internal machines for building, testing, customer support, material development, parameter development, things like that, that we're actively working on. So what this looks like on an actual machine platform basis is we have a series of machines. So from small to large, from limited temperature to a higher temperature production, and basically, if you line them up like this, you see this kind of small series all the way up to production platform, and that will then drive your productivity also. So maybe some of you are familiar with our Formiga P110. It's a smaller machine. Very fine details, and a very good machine for build features and build detail, and all the way up to our production machines, which are larger platform. Now, some of these are focused on a narrower window of build temperatures, and some of our newer machines, which are the P4 and the P5 that are on here, are designed actually to accommodate materials that are typical, such as the nylons, but also up to 300 degrees C, which would then accommodate higher grade materials such as PEKKs and things like that. And so, so we really do see as, and I think the demand, honestly, of our customers over time has been, hey, we need some more flexibility on what materials we can run in which machine. And so our newest platforms are an answer to that, where we want to be enabling that material selection through new advanced and through more flexible machines that can accommodate that. And so a single system hasn't been able to this point to be able to accommodate all materials, but we think that as time goes on, that's what our real strategy is, to include or to increase the options that our customers have. So P4, P5, the P400 is released in North America, and we're shipping machines, and that is the machine that we're really leveraging for some of our material development projects with our customers. So it has a roller system and a different powder feeding system and different heating system that's ultra sensitive and allowing us to develop new custom materials on there. So what does our portfolio look like? This is, when I was putting some of this together, it got a little bit messy, but I wanted to kind of show the general take-home message of this is that, yes, we have our traditional PA12s and PA11s, and we're building on those constantly, basically by differentiating differentiating new composite materials, new compounds that allow specific functions such as ESD, such as FR, things like that. But we're also building into these new material spaces, and so we're actively working on things like polypropylenes that are more of commodity plastics that have not been on the market successfully in the past to release on our platforms, and also the polycarbonates and PA6s, all the way up to the PEKK composites that we already have a product on the market, but we're still differentiating via the ability to change our filler content and the way we process parts to meet very specific opportunities of our customers. And one point I wanted to drive home is we're working on enabling a lot of different resin technologies on our machine. But really, if you take a step back, the base resin is just the beginning of the development. Take a PA11, for example. A nylon 11 has a relatively specific mechanical property range, temperature range, stiffness range, things of that sort. It's only when you start looking into the filler content and that we actually can unlock a lot of ability to customize for a specific application. Some customers want a material and need a material that is extremely stiff with no give whatsoever, and we have fillers for that, and we have processes to produce that material. Some don't. Some need an EOS material, things like that, and so ESD material. And so I think the take-home message is just looking at, I know there's no numbers on here, but just looking at the agents we have and the ability to customize materials, not just based on the base resin, but also based on our filler content, is very powerful. And now that we have, I think, several machines in our portfolio that can accommodate a wider range of materials, we're also unlocking this capability with our customers to really start honing in on application-specific needs. So some of the materials we generally, classifications that we generally work on are conductive. So often customers need jigs, fixtures, things like that are electrostatically dissipating, that don't build up charge and then dissipate rapidly. That's something that can then continually be not building up charge and releasing charge as that builds. And flame retardancy is something that we're continually building new flame retardant materials for applications, and there's different applications such as aerospace, which tend to use different flame retardant technology that maybe isn't appropriate for consumer electronics, and then there's consumer electronic type applications, which is different. UV stability, lubricated, so things that are going to be in a high friction environment that really we need to reduce the amount of wear on the surface, and also generally reinforced for one purpose and another, whether that's improving the tensile strength, improving the stiffness, and things like that. And one point I also wanted to make is one question that we do get a lot, in a discussion that we continually have, is the injection molding conversation. And I think this was made several times on a couple other talks during this conference I've seen. 3D printing is not necessarily, and laser sintering also is not necessarily a direct replacement for all injection molding applications. It can be extremely complementary, whether it's from a low to mid-size build for something that is ultimately going to be ramped up, or something that's never going to be ramped up because of the complexity of the parts, or because of the turnaround time necessary, or the continual innovation on those parts. And so we strongly believe it's not always one or the other. They're often complementary. And when we talk about materials, there very rarely is an injection molding material that is one-to-one with a laser sintering material. So when we're talking a PA6 that's been in an auto spec for 50 years, it's not necessarily that if you find a way to powderize that material and throw it in a machine that you're going to get the same part performance. It could be that a completely different material with a filler content in it can achieve that same performance, but it might be a different base resin or something like that. So what we're really focusing on is how do we help go from a concept with these toolboxes that I've kind of overviewed in the past slides? How do we go from an idea, an application idea, or an application requirements into understanding if our technology is going to be a good fit? And so one way we do this is our applications group, Additive Minds, works with our customers to help understand not just the technology fit, but also the business case fit, and how do we actually understand the costs from a holistic perspective besides just material, and how do we understand the costs of integrating additive, and how do we do that effectively? And also, often it's the case that we don't just need to show that we can build a part that meets a spec. We also need to help qualify those parts internally for our customers. And so this is something that we do a lot of work with our customers to not only drive the getting started on the applications and also the part portfolio evaluation, but we also drive it through helping to set up facilities, production planning, monitoring machine part performance. How do we then be taking regular samples and testing data to ensure that our production is at a quality that is required, and internally help our customers internally certify that process. So we aim to assist in that entire process, not just selling a machine and a material, but helping to sell and develop the entire production solution there. And so the way we typically do this is by developing a custom development path for each application, for each customer, helping to screen specific application and develop that through a custom roadmap, ramping up production and certifying and scaling production. Often we're also able to assist with the ramp up of production by setting up a kind of internal incubator hub in which we'll develop the entire production process with our customers, and then we'll transfer that process to them so that there's less issues with the transfer and more knowledge share. And one of the ways we do that is helping to understand the cost internally for our customers, and how to generate value from building an additive part that maybe traditionally was built another way. So of course there's an added cost up front of additive manufacturing. Some of the materials tend to be more expensive, things like that. But by improving upon the life cycle, the part performance and things like that, we can achieve a net value if we're looking at our leading indicators and our leading differentiators to help us add that value. So there's a lot of value to be gained, but often you have to go and find it with additive. And some of that comes through things like leveraging our ability to have almost limitless complexity. So parts that are high surface area to volume, things that traditionally you can't just pop in an injection molder or machining machine and just build those parts. And customized lightweight construction and individualization is some of those things that we really capitalize on to build that value. And on a value chain side, we capture that lead time reduction and reduction of assembly steps. I talked about that a little bit earlier. But it's really also not just a bill of materials comparison. Oh, this one's cheaper than this. No, it really comes down to the human capital, the ability to innovate, the reduction in inventory, which frees up much more capital in our hands, and having just generally less money tied up in the production and storage of parts and spared parts. So what a typical kind of, I think, roadmap would look like is, sitting down with a customer, understanding their applications, defining a project team, enabling through trainings and design for additive manufacturing understanding, but also digging deep into how do we design our factory layouts, and what technical requirements does the facility need first in order to really streamline production in the future when when production is on its feet and going at full speed. And then we also work on the application development and process parameters specific to that application, specific to that environment. And that's often where some of that I was mentioning earlier, some of the custom material development to meet a specific need comes in. Maybe we have a standard product that is within range of what we need for our application. Well, we have quite a few knobs and things that we can tune on our material and on our process to capture the performance that we need for a given product. So I just wanted to also highlight I think I've only got a few minutes left here, highlight an example of this, a recent example that we've been working on for quite some time, or a year or two here at EOS. Atrex, some of you on the line may have heard of Atrex before. Atrex is a company that produces high quality custom orthotic insoles for their customers. And this is a very, very time consuming and costly process. And it traditionally is custom to their customers, but it also, you're pretty much starting with scratch every time and making these very custom. And so the issue is that over time, the lead times of these products are much higher. The cost tends to be higher. Well, it's really a perfect application for laser sintering, because we're able to take those inputs from our customers, you know, what foot contours they have, what needs they have, and funnel those into a build setup and build them on more of a mass scale. So we can maybe build 100 or so of these at one time, and also on a mass level. So we've teamed up with Atrex, and basically the way we're doing this is through Atrex foot scanners. So what will happen is a user will step into these foot scanners, do a number of different stances and things like that in the scanner. It will read the pressure reading on the bottom of your feet. And we've developed an algorithm to take that pressure reading and basically translate that into unit cell geometries on the bottom of this sole that will then translate into the amount of pressure the sole puts back onto the bottom of your foot. So essentially that is as customized as you get, from taking a reading all the way to building a specific part to balance out your specific pressure profile. And what that's allowed us to do is really to reduce the lead time to just several days to a week, where it was a month to 2 month or several month process. And this also allows the customer to order, as time goes on, new insoles that then are responsive to the changes in the user.
Cary, can you hear me?
Yes.
So we're gonna go quick to the Q&A. We have a few questions. I think we only have time for one.
Okay, great. Well, this was my last slide anyway. So just a custom helmet application also that is very similar, and we're distributing these manufacturing with Hexer over to our customers based on their user profiles.
Okay, so the most voted question is EOS adopting an open source material platform to enable faster innovations in application-specific material? So
that's a very good question. Our general trend is towards allowing, or not enabling, more materials on our machines in any way that we can. The one caveat to that is understanding the effect that any material can have on a machine. So some materials that are relatively unknown can cause damage on a machine and things like that. And so the way we're doing that is really a hands-on approach to enabling our customers, and yes, opening our machines up much more to then allow those custom parameters to be tried on third-party materials and things like that.
Cool. Thank you so much for being here with us today, and I hope you're enjoying them. Thank you.
Thank you very much.